Dear students, welcome to the 14th online class of Control System Engineering. In last class, we started the chapter of block reduction. If a system consists of various subsystems, in this chapter we will find out how to find a single transfer function for this system. Then we started block representation of a system, in which a block with a transfer function represents a system where arrow represents the direction of signals. Then we studied various elements like pickoff point and summing junction. Then we studied various topologies for reducing a complicated system to a single block. These topologies include cascade form, parallel form, and feedback form. If any arrangement of subsystem is not in any of these forms, then we use moving of block across pickoff point and summing junction to make the desired form, and then we reduce the system to single block form. Dear students, after this lecture, you will be able to convert a block diagram into a signal flow graph representation, and then you will learn how to find transfer function using Mason rule for signal flow graph representation. Dear students, contents of this lecture are signal flow graph and Mason's rule. Dear students, signal flow graph is an alternative approach to represent multiple subsystems. In block form of representation, block was used to represent a system where signals were represented by arrows and summing junction and pickoff points were used. The signal flow graph representation consists of only branches which represent the systems, and we have nodes which represent the signal. In figure 1, a block diagram representation is used. In A part, signals are represented with arrows, where in B part, a system is represented in block diagram form, with arrows showing the direction of signals. Now in figure 2, we have a representation in signal flow graph form. In A part, a system is represented with a branch, and its transfer function is shown with arrowhead, where in figure B, a node represents a signal. Dear students, now we will study in detail about signal flow graph representation. A signal flow graph representation consists of nodes and branches. In this, the nodes represent signal, where branches represent the systems. Branches are labeled with transfer function and nodes are labeled with signal names, and the arrow indicate the direction of flow. If two branches are entering to a single node, this node will also perform the function of a summing junction, and you have to conscious with the sign of the signal or the branch gain. Students, branches labeled with transfer function are also known as branch gain. If you look at the figure, in this, a feedback form of system is represented in signal flow graph representation, where R of S is input and C of S is output. Here, the signals are represented in the form of node. Another node we have is E of S, which is error. In this node, we have two branches entering, one with positive sign and another with negative sign. So in calculations, you have to consider the branch gain signs. and this node also acts as a summing junction. Dear students, in block form of representation we have blocks, signals, pickoff point and summing junction, where in signal flow graph we have only branches and nodes. If you look at the figure A, it represents a branch which corresponds to a transfer function of a system G of S. Figure B represents a signal V of S, and the figure C represents interconnection of various signals and system. In this, each signal is the sum of signal flowing into it. In figure C, we have 7 nodes which corresponds to 7 signals: R1 of S, R2 of S, R3 of S. Signals from these nodes are entering into a node V of S. R1 of S is connected to node V of S with a branch having gain of G1 of S. R2 of S is connected to V of S with a branch having gain of minus G2 of S, and R3 of S is connected to V of S with a branch gain of G3 of S. Now we have 3 output nodes, C1 of S, C2 of S and C3 of S. C1 of S is connected to V of S with a branch gain of G4 of S. C2 of S is connected to V of S with a branch having gain of G5 of S, and C3 of S is connected to V of S with a branch having gain of minus G6 of S. Here the node V of S acts as a summing junction, and on further simplification you can find the relation of C1 of S, C2 of S and C3 of S in terms of R1 of S, R2 of S and R3 of S by substituting the value of V of S, which is given in the slide. Dear students, now we will study how to convert a block diagram form of representation into a signal flow graph. For this conversion, first of all you have to identify all the signals present in the block diagram, and then label all these signals in block form of representation. Now, corresponding to each signal, you have to draw a node, and then you have to connect all these nodes with the branches in the place of blocks. While connecting these branches, you have to maintain the direction in which signals are moving. Secondly, label all branches with the corresponding transfer function, and label negative transfer function as necessary to provide negative feedback. And if desired, you can remove redundant nodes, and this will further simplify the system. Or any further simplification possible, you must apply it. Dear students, in the next example, we will study how to convert the block form of series, parallel and feedback system into signal flow graph representation. In each case, we will start by identifying all the signal presents in the block form and then labeling these signals and drawing node for each signal, and finally connecting these nodes with the help of branches. And if any simplification was possible, we will apply it. Now if you look at the figure 1, in this we have 3 systems, G1 of S, G2 of S and G3 of S are connected in series with input R of S and output signal C of S. The intermediate signals present in the system are x1 of s and x2 of s. So for these four signals, R of s, x2 of s, x1 of s, and c of s, we will plot four nodes, and then with the help of the transfer functions, we will connect these nodes. If you see the figure 1, x2 of s is the output of a system g1 of s, where input is R of s. So x2 of s will be connected to node R of s with a branch having gain of g1 of s. Again in figure 1, block having transfer function g2 of s has output of x1 of s and input x2 of s. So in signal flow graph representation, x1 and x2 nodes will be connected with the branch having gain g2 of s. Now again in figure 1, third block have transfer function g3 of s and output signal c of s and input x1 of s. So x1 of s and c of s will be connected with a branch having gain of g3 of s, and this will complete Dear students, now we will study how to make signal flow graph representation for parallel and feedback form. Starting from parallel, if you look at the block diagram form, in this we have three systems G1 of S, G2 of S and G3 of S connected to a common input R of S. Output of G1 of S is X1 of S. Output of G2 of S is X2 of S. And output of G3 of S is X3 of S. All these three signals are summed together to form C of S. So in block diagram form, we have a total of 4 signals. So for these 4 signals, we will plot 4 nodes corresponding to input node R of S, X1 of S, X2 of S, X3 of S, and an output node of C of S. Now we will make connection of these nodes as per block diagram. Node X1 of S and R of S are connected with system G1 of S, so there will be a branch with a gain of G1 of S. Node X2 of S and R of S are connected with the system G2 of S. These nodes will be connected with a branch gain of G2 of S. Similarly, X3 of S and input node R of S are connected with system G3 of S. So between these, there will be a branch with a gain of G3 of S. Now in block form, output is summed to form system output C of S. So in signal flow graph, all the outcomes from these nodes will enter to the output node C of S, which here will act as a summing junction. And these branches will have unit gain. Figure C represents node for the parallel system, and figure D represents nodes and branches for parallel system. Now if you look at the block diagram of feedback system, in this we have input R of S, output C of S, a feedback path with transfer function H of S, and in this error is also calculated. First of all, we will find all the signals. In this we have input signal, error signal and output signal. So for these 3 signals, we will draw 3 nodes. Now input node and error nodes are connected with unit gain. Error node and output node are connected with transfer function g of s, so there will be a branch with a gain of g of s. In feedback path, output node and error node are connected with transfer function h of s, and here output value of h of s is being subtracted from input r of s, so e of s node will act as a summing junction, and the branch connecting c of s and error will have gain of minus h of s. Figure E represents nodes for feedback form, where figure F represents. Dear students, in this example, we will convert a block diagram of system into a signal flow graph. For this conversion, first of all you have to identify all the signals present in the system. And corresponding to each signal, you have to draw a node. If you look at the figure, in this system we have input signal R of S, output signal C of S, and intermediate signals which starts from V1, V2 up to V8. So we have a total of 10 signals present in this system. So for these 10 signals, we will draw 10 nodes as shown in the figure. Dear students, now after drawing the nodes, we will connect these nodes as the systems are connected to the signals in block diagram form. Input node is connected to V1 of S with gain 1. V2 of S is connected with V1 of S with branch gain G1 of S. V3 of S is connected to V2 of S with branch gain 1. V4 of S is connected to V3 of S with branch gain G2 of S. V5 of S is connected to V4 of S with branch gain 1, and output node C of S is connected to node V5 of S with branch gain G3 of S. Now if you look at the block diagram, there is a branch which connects V3 of S to V5 of S. So in signal flow graph, we have a branch which will connect node V3 of S and V5 of S, and it will have unit gain. Now again, if you see the block diagram form, in this we have 3 negative feedback systems: H1 of S, H2 of S, and H3 of S. So their connection will be like C of S node will connect V8 of S node with branch gain H3 of S, and V8 of S node will connect to V5 of S node with -1 gain. Similarly, V4 of S node will get connected to V7 of S node with branch gain H2 of S, and V7 of S node will be get connected to V3 of S with a branch gain -1. And in last, V4 of S node will be connected to V6 of S with branch gain H1 of S, and V6 of S node will be connected to V1 of S with branch gain -1. Now after completing this representation, we will look for that any further simplification is possible or not. If you look at node C of S and V8 of S, these are connected with branch gain H3 of S, and V8 of S V8 of S is connected to V5 of S with branch gain -1. So if we remove V8 of S and make a single branch of gain minus H3 of S, so one node from the system will be reduced, and V8 of S is our redundant node, which means that removing this node won't affect the system response. In the similar way, if you look at the node, V4 of S and V7 of S are connected with branch gain H2 of S, and V7 of S is connected to V3 of S with a branch gain -1. So if we remove node V7 of S and make a single branch of gain minus H2 of S. And similarly for node V4 of S and V6 of S, we'll remove the node V6 of S and make a single branch which will connect node V4 of S and V1 of S with a branch gain of minus H1 of S. Now with this, we complete the signal flow graph representation of a system. Our final system is shown in the figure C. Dear students, now we will study Mason rules. Mason rule is a formula used to calculate single transfer function of overall system. In block reduction technique, we were using parallel form, series form, and feedback form to calculate single transfer function of the system. Where in signal flow graph, we will use Mason rule to calculate the single transfer function of a system. Before applying Mason's rule formula, we will study some basic terms related to this formula. Dear students, first term associated with Mason rule is to define input node. Dear students, first term associated with Mason rule is to define input node. A node having all outgoing branches is known as input node. Second is output node. A node having all incoming branches is known as output node. Next is forward path. A path that starts from input node and ends on output node of the system in signal flow graph without repeating a node is known as forward path. And forward path gain is product of gains found by traversing a path from input node to the output node of the signal flow graph in the direction of signal flow. Dear students, other terms associated with Mason rules formula are loop. Loop is a path that starts and ends on the same node, following the direction of the signal flow without passing through any other node more than once. Next term is loop gain. Loop gain is the product of branch gains found by traversing a path that starts at a node and ends at the same node. Students, next term is non-touching loops. All those loops that don't have any node in common are known as non-touching loops. Now non-touching loop gain is the product of loop gains from non-touching loops taken 2, 3, 4 or more at a time. Students, now in upcoming example, we will use these terms. Dear students, in this example, we have to find out single transfer function for a given signal flow graph representation. First of all, we will define input and output node. As a node having all outgoing branch is known as input node, so R of S in this case is our input node. Similarly, a output node is a node which have all incoming branches. So if you see the figure, C of S is the node which have only incoming branches. So C of S is our output node. Dear students, now we will find out forward path and their gains for this system. A path which starts from input node and ends on output node and without passing through any other node more than once in signal flow graph is known as forward path. In an example, first of all you have to identify how many forward paths exist in a system. In this system, we have two forward paths which connects input and output without repeating a node. First forward path start from input node R of S and then move along the nodes V5 of S, V4 of S, V3 of S, V2 of S, V1 of S and ends on output node C of S. Similarly, we have second forward path which starts from input node R of S and then move through V5 of S, V4 of S, V3 of S, V2 of S, V1 of S and C of S. Apparently both forward paths are same. Now look at their forward path gains. First forward path have a gain of G1 of S, G2 of S, G3 of S, G4 of S, G of S, G5 of S and G7 of S. Where second forward path have gain of G1 of S, G2 of S, G3 of S, G4 of S, G6 of S and G7 of S. In this example, nodes involved in the forward path are same, but their forward path gain is different, or a one branch is different. So these are the forward paths and their gains. Now we will find loops and their gain. For example, any closed path which starts at end on the same node without passing through any other node more than once is known as a loop. Students, first of all you have to find out how many loops or a closed path exist in a system. Loop 1 starts from V5, then goes to V4 and ends on V5. And it have a loop gain of G2 of S into H1 of S into H1 of S. Loop 2 start from V3 of S, then goes to V2 of S and ends on V3 of S. And it have a loop gain of G4 of S into H2 of S. Loop 3 starts from V3 of S, goes to V2 of S, V1 of S and again ends on V3 of S. And it have a loop gain of G4 of S, G5 of S into H3 of S. Similarly, the last loop starts from V3 of S, goes to V2 of S, V1 of S and ends on V3 of S. And it have a loop gain of G4 of S, G6 of S product with H3 of S. So these were the loops and their. Dear students, now we will study about non-touching loops and their gains. Loops that don't have any node in common are known as non-touching loops. And product of loop gains from non-touching loops taken 2, 3 or more is known as non-touching loop gain. If you see the figure, in this system we have a total of 4 loops and 3 of them have a common node, which means that loop 2, loop 3 and loop 4 are sharing a node, where loop 1 don't share any node with loop 2, loop 3 or loop 4. So loop 1 and loop 2 is our first non-touching loop, and the product of their loop gain will form non-touching loop gain. Similarly, loop 1 and loop 3 is our second non-touching loop, and the product of gain of loop 1 and loop 3 will form second non-touching loop gain. Now loop 1 and loop 4 is our third non-touching loop, so product of loop gain 1 and loop gain 4 will form third non-touching loop gain. Now with this we have complete the terms related with Mason's rules. Now we'll use the formula to find single transfer function for the system. Dear students, now we will apply Mason's rule formula to find out single transfer function for a given signal flow graph. In this formula, transfer function is equal to sum of forward path multiplied by del case divided by delta. Now in this formula, k is equal to number of forward path and tk represent kth forward path gain, and delta is equal to 1 minus sum of loop gains plus sum of non-touching loop gains taken 2 at a time minus sum of non-touching loop gains taken 3 at a time plus sum of non-touching loop gains taken 4 at a time, and so on. And delta k is equal to delta minus sum of loop gain terms in delta that touch the kth forward path. Student, it is a predefined formula in which we all have to substitute the values. Now we will substitute the values for a given. Dear students, in the given example, we know that we have 2 forward paths, so k will be equal to 1, 2, and their forward path gains are represented by T1 and T2, where T1 is equal to product of G1 of S, G2 of S, G3 of S, G4, G5 and G7. Similarly, T2 is product of G1, G1, G2, G3, G4, G6 and G7. Now delta is equal to 1 minus sum of loop gains plus sum of non-touching loop gains taken 2 at a time minus sum of non-touching loop gains taken 3 at a time. In this case we have sum of non-touching loop gains taken 2 at a time. So substituting their loop gains, we will get value of delta. Now for each forward path we have delta 1 and delta 2. Both are equal to 1 because del k is equal to delta minus sum of loop gain terms in delta that touch the kth forward path. Now if you see all the loop gains are connected to first forward path, so del 1 will be equal to 1, and similarly all the loops are connected to second loop. Similarly del 2 will also be equal to 1. Now substituting all these values in the transfer function, we will get our desired single transfer function for the system using Mason's rule. Now if any of you have any questions, please ask.